planet we thought we knew. For most of the 20th century, Pluto existed in the human mind as something certain. It was small, distant, cold, and alone, circling the sun far beyond the familiar worlds of the inner solar system. It was taught in classrooms, printed in textbooks, and memorized by generations of students as the ninth planet, the last stop in an orderly cosmic family. Pluto felt settled, defined, understood. And yet, almost everything we believed about Pluto was shaped not by evidence, but by assumption. From the moment Pluto entered public awareness, it carried expectations that science had not yet earned. It was labeled a planet long before anyone truly knew what kind of world it was. Its size, composition, atmosphere, and behavior were largely unknown. But the label stuck, and with it, a powerful narrative. While Pluto became more than an object in space, it became an idea. In the human imagination, Pluto represented the edge, the boundary between the known and the unknown. It was the final dot on the solar system map, the quiet world at the end of the line. And because it was far away, it was easy to leave it there. Distant, static, and uncomplicated. But distance has a way of hiding complexity. For decades, Pluto was little more than a faint point of light in telescopes. Even the largest instruments on Earth could reveal almost nothing beyond its orbit and brightness. Scientists estimated its size indirectly. They inferred its mass. They guessed at its composition. Every fact about Pluto was filtered through uncertainty. Yet certainty entered the story anyway. Pluto was called a planet because it fit a historical expectation, and not because it fit a scientific definition. And once that label was applied, it shaped everything that followed. Pluto was compared to planets, judged like planets, expected to behave like planets. When it didn't, confusion followed. But rather than question the label, scientists and the public alike often questioned Pluto itself, as if the problem lay with the object, not the category. This is where the misunderstanding began. Pluto's story is not one of failure or demotion. It is a story of evolving knowledge and of how human attachment to labels can obscure reality. To understand Pluto, we must first understand how deeply perception shapes science. When Pluto was discovered in 1930, astronomy was in a transitional phase. Telescopes were improving, but still limited. The outer solar system was largely unexplored, and there were no spacecraft, no detailed imaging, no direct measurements. Pluto appeared as a moving speck against the background stars, proof of existence, but little else. At the time, scientists were searching for a ninth planet. Observations of Uranus and Neptune suggested gravitational irregularities, leading astronomers to suspect another massive object farther out. Pluto was discovered during this search, and despite being far smaller than expected, it was quickly accepted as the missing planet. This acceptance mattered more than accuracy. Once Pluto was placed into the planetary lineup, few questioned whether it truly belonged there. It became planet number 9 by historical momentum, by tradition, by convenience. And tradition is powerful. Pluto entered school curriculums. It entered culture. It became part of childhood memory. In its name, chosen by a young girl, gave it personality. It was no longer just an astronomical object. It was Pluto, the planet at the edge of everything. But science does not run on memory. As technology advanced, cracks began to form in Pluto's planetary identity. Measurements improved. Pluto's estimated size shrank. Its mass proved to be far smaller than anyone had imagined. It became clear that Pluto was not the gravitational heavyweight once thought necessary to explain planetary motions. Pluto was not the missing giant planet. Still, the label remained. This reluctance to change was not rooted in stubbornness, but in uncertainty. Scientists had not yet seen enough of the outer solar system to know what Pluto truly was. Without context, Pluto stood alone. There was nothing obvious to compare it to, and it is difficult to classify something when it appears unique. So Pluto remained a planet, not because the evidence supported it, but because there was no alternative framework yet. As years passed, Pluto's orbit raised more questions. It was highly elongated. It was tilted far from the plane of the other planets. At times, Pluto even crossed inside Neptune's orbit. These behaviors were unlike those of the classical planets. But Pluto was stable. Its orbit was locked in resonance with Neptune, preventing collisions. This stability reassured astronomers, but it did not solve the classification problem. Pluto was behaving like something else. The truth is that Pluto was never meant to fit neatly into the planetary category. That category itself was built around the inner solar system. Large, dominant bodies that had cleared their neighborhoods and followed orderly paths around the sun. Pluto did none of these things, yet the expectation persisted. Pluto's story reveals something fundamental about how humans understand the universe. We prefer neat categories. We prefer lists with clear boundaries. We like to believe the solar system is simple, hierarchical, and complete. But the universe does not care about our lists. Pluto exists where categories blur. It sits in a region of space that preserves the remnants of planetary formation. A cold, distant zone filled with icy worlds that never became planets in the traditional sense. For most of the 20th century, we did not know this region existed. Pluto seemed lonely because we had not yet discovered its neighbors, and this loneliness reinforced the idea that Pluto was special, a singular planet at the edge. In reality, Pluto was part of a much larger population, hidden beyond the limits of early observation. The misunderstanding of Pluto was therefore not a failure of observation, but a failure of context. Without context, Pluto looked like a planet. With context, it looks like something else entirely. And this shift in perspective would change planetary science forever. But before that change could happen, Pluto had to become emotionally entrenched. The longer it remained a planet in public consciousness, the harder it would be to revise that identity. Pluto became symbolic, a symbol of discovery, of curiosity, of the outer frontier. Removing that symbol would feel like loss. This emotional attachment explains why Pluto's reclassification later triggered such strong reactions. People felt something had been taken away, a planet erased, a memory rewritten. But science does not erase, it refines. Pluto did not change, our understanding did. Pluto was never reduced, it was revealed. The truth is that Pluto is not small in significance, it is not simple, and it is certainly not boring. Pluto is one of the most complex, surprising, and scientifically valuable worlds in the solar system. But to see that, we must first let go of the idea that Pluto failed to be a planet. Pluto never failed. Our expectations did. The accidental discovery Pluto was never supposed to be found the way it was. Its discovery did not come from a dramatic breakthrough or a bold new theory. It emerged instead from persistence, patience, and a search based on assumptions that later proved incorrect. Pluto entered astronomy almost quietly, as a solution to a problem that did not truly exist. At the beginning of the 20th century, astronomers believed the solar system was incomplete. Uranus and Neptune, the two outermost known planets at the time, showed slight irregularities in their orbits. These deviations were interpreted as gravitational disturbances caused by an unseen planet farther out. The idea was reasonable. Neptune itself had been discovered using similar logic. Mathematical predictions had pointed to its position before it was ever observed. This success reinforced confidence in the method. If Neptune could be found this way, why not another planet beyond it? This hypothetical object became known as Planet X. Planet X was expected to be massive, large enough to influence the orbits of known planets. Astronomers imagined something comparable to Neptune, or even larger. It would be dark, distant, and difficult to spot, but its gravitational pull would betray its presence. The search began with expectations already set. In Arizona, at Lowell Observatory, the task of finding Planet X fell to a young astronomer named Clyde Tombaugh. Tombaugh was meticulous, patient, and skilled at a method that required extraordinary attention to detail. He compared photographs of the night sky taken days or weeks apart, searching for any object that shifted position against the fixed background of stars. This work was slow and exhausting. Thousands of images passed through his hands. Then, in 1930, Tombaugh noticed a tiny moving dot. That dot was Pluto. At first, Pluto appeared to confirm the existence of Planet X. It moved as expected. It was distant. It was real. The discovery was announced, celebrated, and quickly embraced by the scientific community and the public alike. But there was a problem almost immediately. Pluto was faint, extremely faint. Its brightness suggested it was far smaller than predicted. Too small, in fact, to account for the supposed gravitational effects on Uranus and Neptune. This inconsistency raised doubts, but excitement overshadowed caution. Astronomers assumed Pluto must be more massive than it appeared. Perhaps it was darker than expected. Perhaps it had a large atmosphere. Perhaps it was simply hard to measure accurately. These assumptions filled the gap between expectation and observation. In reality, the original problem, the irregular orbits of Uranus and Neptune, was itself flawed. Later measurements would show that the discrepancies were caused by inaccuracies in earlier data, not by an unseen planet. Planet X did not exist in the way astronomers imagined. Pluto had been discovered during a search for something else entirely. This accidental discovery shaped Pluto's fate. Because Pluto was found while searching for a planet, it was assumed to be one. The context of its discovery mattered more than the object itself. The label came first. Understanding followed much later. This sequence is unusual in science, but not unheard of. Discoveries often outpace explanation. Objects are found before their nature is fully understood. What makes Pluto's case unique is how long the assumptions persisted. For decades, Pluto remained poorly understood. Its distance made observation difficult. Even as telescopes improved, Pluto's small size and faint light limited what could be seen. Its diameter estimates varied wildly. Some estimates suggested it was nearly as large as Earth. Others placed it closer to Mars. No one knew for sure. As a result, Pluto existed in a state of uncertainty disguised as certainty. It was listed as a planet, but no one could describe it with confidence. Its mass was eventually measured more accurately after the discovery of its largest moon, Charon, in 1978. This discovery allowed astronomers to calculate Pluto's mass based on orbital dynamics. The result was shocking. Pluto was tiny. Its mass was only a fraction of Earth's moon. Far too small to influence Neptune or Uranus. Far too small to match the expectations placed upon it. This should have triggered immediate reclassification. It did not. Why? because Pluto had already become familiar. By the time its true size was known, Pluto had been a planet for nearly 50 years. It had entered culture, education, and identity. Reclassifying it would require redefining what a planet was, something science had never needed to do formally before. The solar system had grown organically in human understanding. Definitions were implicit, not explicit. Pluto exposed the weakness of this approach. It forced astronomers to confront a fundamental question they had avoided. What, exactly, is a planet? Until Pluto, the answer seemed obvious enough not to require precision. After Pluto, vagueness was no longer sufficient. Pluto's accidental discovery also highlights how observation bias shapes knowledge. Astronomers were looking for something specific, so when they found something vaguely similar, they interpreted it through that lens. This bias is human, not malicious. Science advances by correcting such biases over time. Pluto simply took longer than most cases. As telescopes improved further and surveys expanded, more distant objects began to appear. These objects shared Pluto's characteristics: small, icy, distant, and oddly orbiting. At first, they were treated as anomalies. Then, patterns emerged. Pluto was not alone. The region beyond Neptune was not empty, as once believed. It was populated by countless icy bodies, remnants of the early solar system that never coalesced into a dominant planet. Pluto was part of this population, but this realization lay decades in the future. In the early years after its discovery, Pluto existed in isolation. It was a planet because there were no obvious alternatives. The outer solar system was still largely invisible. Pluto filled a gap in imagination more than in evidence. Its accidental discovery meant that its identity was shaped by coincidence rather than classification. It was discovered at the right time to be called a planet, but not at the right time to be understood properly. This timing would have lasting consequences. Pluto's story shows that discovery alone does not equal understanding. Finding an object is only the first step. Interpreting it correctly requires context, comparison, and patience. Pluto lacked that context for most of the 20th century. As a result, it carried a label that never truly fit. And yet, Pluto itself was never wrong. It orbited as it always had. It behaved according to physics, indifferent to human categories. The misunderstanding was ours. Why Pluto was never like the other planets. Even before Pluto lost its planetary status, the evidence was already there. Quiet, persistent, and often ignored. Pluto never truly behaved like the other planets. Not in its motion, not in its orientation, and not in its relationship with the rest of the solar system. Pluto was always different. The classical planets follow a familiar pattern. Their orbits lie roughly in the same flat plane, known as the ecliptic. This shared plane reflects the disk of gas and dust from which the solar system formed. Their paths around the Sun are mostly circular, stable, and predictable. Pluto does not follow this pattern. Its orbit is steeply inclined, tilted more than 17 degrees relative to the plane of the planets. This alone sets Pluto apart. It does not travel alongside the others, but above and below them, cutting through space at an angle that feels almost defiant. This tilt is not subtle, it is extreme. Such an inclination suggests a very different origin story, one shaped by interactions, disturbances, and early chaos. Objects that form peacefully within a disk tend to remain aligned. Objects that are scattered, captured, or disturbed do not. Pluto's orbit carries the signature of disruption. Its path around the Sun is also highly elongated. While most planets trace nearly circular orbits, Pluto follows a stretched ellipse, At its closest approach to the Sun, Pluto comes closer than Neptune. At its farthest, it drifts deep into the cold darkness beyond. For part of its long year, which lasts 248 Earth years, Pluto is closer to the Sun than the eighth planet. This behavior alone should have raised alarms. Planets are supposed to dominate their regions. They clear their orbital paths of debris. They exert gravitational authority. Pluto does none of this. It shares its region with countless icy bodies, many of which follow similar paths. Pluto does not rule its neighborhood. Instead, it moves within it. This distinction matters more than size alone. A planet is not just a body that orbits the Sun. It is a body that shapes its surroundings. Pluto is shaped by its surroundings instead. Its interaction with Neptune further emphasizes this point. Pluto's orbit crosses Neptune's path, yet the two never collide. This is not luck. It is resonance. While Pluto and Neptune are locked in a precise gravitational dance known as a 3-2-2 orbital resonance. For every 3 orbits Neptune completes, Pluto completes 2. This rhythm keeps them safely separated, even though their paths intersect in space. Resonance is common among smaller bodies, asteroids, comets, and icy objects influenced by larger planets. It is not typical behavior for planets themselves. Pluto behaves like a captured object, not a dominant one. Its rotation adds another layer of strangeness. Pluto spins on its side, with an axial tilt of over 120 degrees. This means that during parts of its orbit, one hemisphere faces the Sun continuously for decades, while the other remains in darkness. Seasons on Pluto are extreme beyond earthly comparison. On Earth, seasons result from a modest axial tilt. On Pluto, they are the consequence of a world almost lying on its side. Temperature gradients shift slowly. Ice migrates across the surface. Atmospheres appear and disappear. This is not planetary behavior as we typically imagine it. Pluto's motion through space is slow, tilted, and eccentric. It does not fit the orderly rhythm of the classical planets. And yet, for decades, this was explained away as a curiosity rather than a classification problem. Why? Because Pluto stood alone. Without context, difference looks like exception. With context, difference looks like category. The truth is that Pluto resembles the worlds of the outer solar system far more than it resembles the inner planets. Its composition is dominated by ice and rock rather than metal and silicates. Its density suggests a mixture typical of icy bodies formed far from the Sun. But Pluto's surface temperature is so low that common gases freeze solid. Nitrogen, methane, and carbon monoxide behave like rock on Earth. This chemistry is alien to the terrestrial planets and even to the gas giants. Pluto exists in a different regime of physics. This regime defines a region of the solar system that was poorly understood for most of the 20th century. Beyond Neptune lies a vast reservoir of icy objects, remnants of planetary formation that never coalesced into a single dominant body. Pluto belongs to this reservoir. Its odd orbit, its composition, and its behavior all point in the same direction. Pluto is not a misbehaving planet. It is a representative of a different class of worlds. The reason this was not recognized earlier is simple. We did not know how many such worlds existed. For decades, Cerber, Pluto was the only one visible. It is easy to mistake the first discovered member of a population as unique. It is much harder to do so once the population reveals itself. As more distant objects were discovered beyond Neptune, Pluto's oddities became patterns. Other bodies shared its inclination. Others followed resonant orbits. Others had similar sizes and compositions. Pluto was no longer alone. This realization forced a shift in perspective. The solar system was not composed of 8 planets and one oddball. It was composed of multiple regions, each with its own dominant processes and populations. The inner solar system is shaped by rocky worlds, the middle by gas giants, the outer by ice-rich remnants. Pluto sits firmly in that outer category. Its failure to resemble the classical planets is not a flaw. It is evidence, your evidence that Pluto formed in a different environment. Evidence that it experienced different gravitational interactions. Evidence that it belongs to a population shaped by Neptune's migration and the early chaos of the solar system. Pluto's differences were not subtle. They were fundamental. But because Pluto was discovered early, before its neighbors, those differences were tolerated rather than understood. This tolerance delayed clarity. The question was never whether Pluto was strange. The question was why we expected it not to be. Pluto's orbit tells the story of a solar system that was once far less orderly than it appears today. Giant planets migrated. Orbits shifted. Smaller bodies were scattered, captured, and trapped in resonances. Pluto survived this upheaval. Its current path is a fossil of that era, a record of migration and chaos frozen in motion. In this sense, Pluto is not a problem for planetary science. It is a gift. It preserves information about a time when the solar system was young and unstable. Its orbit is a clue. Its tilt is a signature. Its behavior is a message. The misunderstanding arose when we tried to force that message into the wrong framework. Pluto does not need to resemble Earth, Mars, or Jupiter to be important. It does not need to clear its orbit to be meaningful. It does not need to fit our expectations. Pluto tells its own story, and that story begins with difference. The myth of the 9th planet. By the middle of the 20th century, Pluto's identity felt unquestionable. It had been called a planet for decades. It appeared in every textbook, and it sat at the end of every solar system diagram, small but proudly numbered. Children learned its name alongside Mercury, Venus, Earth, and the rest. Pluto was not just accepted, it was familiar, and familiarity is powerful. Once an idea settles into culture, it gains weight beyond evidence. Pluto's status as the 9th planet was reinforced not by data, but by repetition. The more it was taught, the more it felt true. The fewer people questioned it, the more permanent it seemed. This is how myths form in science, not through deception, but through inertia. The myth of Pluto as the 9th planet did not arise because scientists ignored evidence. It arose because no one had yet assembled the full picture. Pluto existed in isolation, and isolation makes classification difficult. With nothing similar to compare it to, while Pluto was judged by the standards of planets simply because those were the only standards available. At the time, this seemed reasonable. But as decades passed, Pluto began to strain against its planetary identity. Measurements showed it was smaller than Earth's moon. Its mass was insignificant compared to the giants it supposedly joined. Its orbit defied the neat architecture of the solar system. Still, the myth endured. Part of the reason was emotional. Pluto had become the underdog planet. Small, distant, and lonely. People sympathized with it. Removing its planetary status felt like punishment, even though science does not assign value that way. Another reason was practical. Redefining Pluto would require redefining planet, a word that had never been rigorously defined. For centuries, the planets were simply objects that moved against the background stars. That definition worked until it didn't. Pluto exposed the limits of tradition. As astronomy advanced, more objects like Pluto began to appear. Improved telescopes revealed icy worlds beyond Neptune. some nearly as large as Pluto itself. Each discovery chipped away at the myth. If Pluto was a planet, what about these others? Were they planets too? Should the solar system suddenly have dozens of planets? Or was the category itself flawed? The myth of the ninth planet began to crack. Scientists found themselves trapped between consistency and clarity. Keeping Pluto as a planet meant expanding the list indefinitely. Removing Pluto meant confronting public backlash and rewriting decades of education. Neither option was comfortable, but science does not exist to preserve comfort. It exists to reflect reality as accurately as possible. The myth of Pluto persisted because it filled a narrative need. Humans like neat endings. Pluto was the final chapter of the solar system, the edge, the last world, the distant frontier. Removing it disrupted that narrative. But the universe does not follow human storytelling rules. The solar system does not end neatly at Pluto. It extends far beyond, filled with countless worlds that challenge simple classification. Pluto was never the end. It was the beginning of a much larger realization. The ninth planet myth also obscured Pluto's true importance. By forcing it into the planetary mold, scientists overlooked what made Pluto special. Its connection to the Kuiper Belt, its role as a representative of a vast population of icy bodies, its value as a time capsule from the solar system's formation. Pluto was treated as a failed planet rather than a successful example of something else. This misinterpretation shaped research priorities. Pluto was not studied as deeply as it deserved. It was distant and difficult to reach. And its planetary status did not guarantee attention. It was assumed to be simple, inactive, and unchanging. That assumption would later prove disastrously wrong. The myth also influenced public reaction when Pluto was reclassified. The narrative was framed as loss, a planet taken away. Headlines spoke of demotion, downgrading, and banishment. These words implied judgment. But Pluto was not judged. It was understood. The myth of the ninth planet reveals a broader truth about science communication. Labels matter. They shape perception. When labels are applied too early or too rigidly, they can distort understanding. Pluto's label lasted too long, yet the myth was not maintained out of stubbornness. It persisted because Pluto's true context remained hidden. Without knowledge of the Kuiper Belt, Pluto looked exceptional. With that knowledge, it looks representative. This shift did not diminish Pluto. It elevated the entire outer solar system. The solar system turned out to be richer, more complex, and more crowded than anyone imagined. Pluto was the first glimpse into that complexity. But first discoveries often bear the burden of misunderstanding. The myth of Pluto as the ninth planet was not a mistake in the moral sense. It was a temporary interpretation based on limited information. What matters is not that the myth existed, but that it was eventually questioned. Our science progresses by letting go. As the 20th century came to a close, evidence mounted. Pluto's orbit, its size, its neighbors. The case for redefinition became unavoidable. The myth could no longer hold. What followed was not an erasure, but a clarification. Pluto would soon force astronomers to do something unprecedented, formally define what a planet is. And that definition would change everything. What a planet really means. For most of human history, the word planet meant very little scientifically. It was a descriptive term, not a precise one. Planets were simply the wandering lights in the sky, objects that moved differently from the fixed stars. This loose definition worked well enough when the solar system was small, familiar, and uncomplicated. But Pluto exposed the weakness of that simplicity. When astronomers first labeled Pluto a planet, they were not applying a rigorous definition. They were continuing a tradition. That tradition had grown organically over centuries, shaped by observation rather than theory. No formal criteria existed. There was no checklist. There was only precedent. This worked when the solar system consisted of a handful of large, dominant bodies. It failed when the solar system turned out to be crowded. As telescopes improved and surveys expanded, astronomers began discovering objects that blurred boundaries. Some were nearly as large as Pluto. Some followed similar orbits. Some challenged assumptions about dominance, formation, and classification. The question became unavoidable. What is a planet? At first glance, the answer seems obvious. A planet orbits a star. It is round. It is large. But each of these criteria breaks down under scrutiny. Many objects orbit the Sun. Asteroids do. Comets do. Icy bodies beyond Neptune do. Orbit alone is not enough. Being round seems intuitive, but roundness depends on composition and temperature. Ice becomes spherical at smaller sizes than rock. A frozen world can be round while remaining relatively small. Should it be a planet simply because it is round? Size alone also fails. There is no natural boundary where planet begins and not planet ends. Nature does not draw clean lines. This ambiguity haunted astronomers as Pluto's neighbors began to reveal themselves. If Pluto was a planet because it was round and orbited the Sun, then many newly discovered objects should also be planets. The solar system would suddenly contain dozens, perhaps hundreds, of planets. And this outcome felt absurd, not because it violated physics, but because it violated intuition. Astronomers realized they needed a definition grounded not in tradition, but in dynamics, how objects interact with their surroundings. This led to a critical idea. A planet is not just something that orbits a star. It is something that dominates its orbit. Dominance means gravitational authority. A planet must be massive enough to clear its orbital neighborhood, to either absorb, eject, or control smaller bodies nearby. Over time, a true planet becomes the undisputed ruler of its region. Earth does this. Jupiter does this. Neptune does this. Pluto does not. Pluto shares its orbit with countless other icy bodies. It has not cleared its neighborhood. It is one of many, not the dominant one. This distinction is not about size or importance. It is about context. Pluto exists in a region shaped by Neptune's gravity, a region filled with objects in resonant orbits influenced by a larger planet. Pluto is subject to this influence. It does not exert it. This realization reframed the debate. Pluto was not being demoted. The definition was being corrected. In 2006, astronomers gathered to formalize what had long been implicit. They proposed a definition of a planet that included 3 criteria: orbiting the Sun, being round, and clearing its orbital neighborhood. Pluto met 2 of these criteria. It failed the 3rd. This failure did not make Pluto lesser. It made it different. The term dwarf planet was introduced to acknowledge this difference. It recognized objects that are round and orbit the Sun, but do not dominate their orbits. Mount Pluto became the most famous member of this new category. Critics argued that the definition was arbitrary, that it was too restrictive, that it reflected human preference rather than cosmic truth. But all definitions are human constructs. What matters is whether they help us understand reality. In Pluto's case, the new definition did exactly that. It placed Pluto in proper context. It connected Pluto to a population of similar worlds. It clarified relationships rather than obscuring them. The controversy that followed revealed a deeper tension between public perception and scientific practice. Many people felt that Pluto's planetary status was intrinsic, something it possessed inherently. But categories are not intrinsic. They are tools. Science uses categories to organize knowledge, not to assign value. When categories stop serving that purpose, they must change. Pluto forced that change. The debate also highlighted how emotionally charged science can become when it intersects with memory and identity. People grew up with Pluto as a planet. Losing that label felt personal. But Pluto did not lose anything tangible. Its orbit remained the same. Its complexity remained the same. Its scientific value remained the same. Only our understanding changed. The question, what is a planet, may seem trivial, but it touches on how humans interpret the universe. We prefer simple hierarchies. We want clear ranks. We like to know what belongs where. The universe does not share that preference. It produces continua, not categories. It creates objects that blur boundaries. Pluto is one of them. By forcing astronomers to define planet, Pluto improved clarity across the solar system. It prevented confusion. It avoided inflation of terminology. It allowed scientists to describe worlds more accurately. Pluto's reclassification was not an end. It was a beginning. It opened the door to a more nuanced understanding of planetary systems, not just ours, but others as well. Exoplanet studies now rely on definitions shaped in part by Pluto's case. Pluto taught us that words matter, that definitions shape discovery, and that clinging to outdated categories can hinder understanding. This lesson extends beyond astronomy. It reminds us that knowledge evolves, that certainty is provisional, and that revision is not weakness, but strength. Pluto did not force scientists to take something away. It forced them to see more clearly the day Pluto was demoted. For many people, the story of Pluto seems to pivot on a single moment. A vote, a decision, a declaration that stripped a planet of its status. In popular memory, this moment is framed as sudden and dramatic, as if Pluto were cast out overnight. The reality was far slower, far quieter, and far more inevitable. By the early 2000s, the pressure to redefine Pluto had been building for years. Astronomers were discovering new objects beyond Neptune at an accelerating pace. Some of them were close to Pluto in size. Others followed similar orbits. One object in particular, later named Eris, appeared to be slightly larger than Pluto itself. This discovery changed everything. If Pluto was a planet, then Eris had to be one too. And if Eris was a planet, then many more objects would soon join the list. And the solar system would no longer have 9 planets, but dozens, perhaps hundreds, depending on where the line was drawn. The problem was no longer theoretical. It was practical. Astronomy needed a definition that could scale with discovery. In 2006, the International Astronomical Union gathered to address this issue formally. For the first time in history, scientists attempted to define the word planet in precise terms. This was not done lightly. The debate was intense, technical, and deeply philosophical. At stake was not Pluto itself, but clarity. The final definition was the result of compromise. It attempted to balance tradition with dynamical reality. According to this definition, a planet must orbit the Sun, be massive enough to become round, and have cleared its orbital neighborhood. Pluto satisfied 2 of these conditions. It failed the third. The vote that followed was not unanimous. Many astronomers disagreed with aspects of the definition. Some felt it was too narrow. Others argued it was incomplete, A few believed the decision should have been delayed. But science does not require unanimity. It requires consensus sufficient to move forward. When the vote passed, Pluto's status changed officially. It was reclassified as a dwarf planet, a term that immediately became misunderstood. The word dwarf was interpreted as diminutive or inferior, even though it describes a category, not a ranking. Pluto was not expelled from science. It was placed where it belonged. The public reaction was swift and emotional. Headlines framed the decision as a loss. Pluto had been demoted, downgraded, or kicked out of the planetary club. Memes, protests, and petitions followed. This response revealed how deeply Pluto had embedded itself in cultural identity. People were not defending a scientific classification. They were defending a memory. For scientists, the reaction was puzzling. Pluto had not changed. Only the language had. Its physical properties, its orbit, its importance, all remained the same. But language matters. Pluto's reclassification exposed a gap between how science organizes knowledge and how the public relates to it. For scientists, categories are tools. For the public, they are stories. And Pluto had been part of a story for nearly a century. The term demotion implies judgment, as if Pluto failed a test. In reality, Pluto never attempted to be a planet. It followed the same orbit it always had. It behaved according to the same physics. The failure was not Pluto's. It was the old definitions. The decision in 2006 did not diminish Pluto's scientific value. In fact, it increased it. By recognizing Pluto as part of a broader population, astronomers could study it as a representative world, a window into the outer solar system rather than an anomaly. Pluto became a key example instead of an exception. The controversy also highlighted how science corrects itself. When new evidence accumulates, definitions evolve. This process is often messy. It involves debate, disagreement, and revision. This is not a weakness. It is the mechanism by which understanding improves. The day Pluto was reclassified was not the day it lost importance. It was the day the solar system gained clarity. Boundaries became meaningful. Categories reflected dynamics rather than tradition. And Pluto's new label connected it to a family of worlds with shared origins and behaviors. It linked Pluto to the Kuiper Belt, a vast, icy region extending beyond Neptune, filled with objects left over from planetary formation. This connection had been obscured by Pluto's planetary status. Once revealed, it transformed how astronomers viewed the outer solar system. The emotional reaction to Pluto's reclassification also revealed something about human nature. We resist change when it challenges familiar narratives. We anthropomorphize objects. We assign them status and identity. Pluto became a victim of this tendency. But Pluto does not care. It continues to orbit the Sun every 248 years. It continues to spin on its tilted axis. It continues to host glaciers, mountains, and an atmosphere that freezes and thaws with the seasons. Pluto did not shrink when it was reclassified. It expanded. It became the most famous representative of a new class of worlds. Worlds that are round, complex, and scientifically rich, yet shaped by environments very different from the classical planets. The day Pluto was demoted was, in truth, the day it was understood. Pluto's strange orbit, Pluto, does not travel through space the way most people imagine a planet should. Its path around the Sun is not neat, not flat, and not orderly. Instead, it follows a route that appears chaotic at first glance, looping, tilting, and stretching in ways that challenge intuition. This orbit is one of the earliest clues that Pluto was never meant to fit among the classical planets. Most planets move around the Sun in orbits that are nearly circular. Their paths lie close to a single plane, reflecting the flat disk of gas and dust from which the solar system formed. This shared geometry gives the solar system its sense of order. Pluto breaks this pattern dramatically. Its orbit is tilted more than 17 degrees relative to the plane of the planets. This means Pluto spends much of its long year traveling far above and below the paths of the other worlds. From certain perspectives, Pluto does not even appear to belong to the same system. This tilt is not accidental. Orbital inclination is shaped early in a system's history. Objects that form quietly within a disk remain aligned. Objects that are scattered, captured, or disturbed acquire tilted paths. Pluto's inclination tells a story of interaction and disruption, of a solar system that was once far more violent than it appears today. Pluto's orbit is also highly eccentric. Instead of tracing a near circle, it follows an elongated ellipse. At its closest approach to the Sun, Pluto is nearly 30 astronomical units away. At its farthest, it drifts beyond 49 astronomical units, plunging into a realm of deep cold and darkness. For part of its orbit, Pluto is actually closer to the Sun than Neptune. This fact alone unsettled astronomers for decades. Planets are supposed to remain in distinct lanes, neatly ordered by distance. Pluto ignores this expectation completely. Yet despite this apparent chaos, Pluto's orbit is remarkably stable. The reason lies in resonance. Pluto and Neptune are locked in a precise gravitational relationship known as a 3-to-2 orbital resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2. This rhythm ensures that the two bodies never come close to each other, even though their paths intersect in space. Whenever Pluto crosses the plane of Neptune's orbit, Neptune is safely elsewhere. This is not coincidence. Resonance is a signature of gravitational interaction over immense periods of time. It implies that Pluto's orbit was shaped by Neptune's migration early in the solar system's history. As Neptune moved outward, its gravity swept smaller objects into resonant configurations. Pluto was captured in this process. This capture tells us something profound. Pluto did not form in isolation. It was shaped by the movement of a much larger planet. Its current orbit is a fossil of that migration, a preserved record of a time when the giant planets shifted positions, scattering icy bodies across the outer solar system. Planets dominate. Pluto responds. This distinction is critical. Pluto's orbit is not one of authority, but of survival. It occupies a niche carved by Neptune's gravity, protected by resonance, but never dominant. This is the behavior of a member of a population, not the ruler of a region. The orbital resonance also explains why Pluto has survived for billions of years without being ejected or destroyed. Without resonance, its crossing orbit would be unstable. Over time, close encounters with Neptune would have altered Pluto's path dramatically. Instead, Pluto's motion is locked into a stable dance, a cosmic choreography maintained over the age of the solar system. This stability does not make Pluto a planet. It makes it a relic. Pluto's strange orbit is shared by many other distant objects, and as astronomers discovered more Kuiper Belt objects, they found similar eccentricities, inclinations, and resonances. Pluto turned out to be one of many bodies following these unconventional paths. What once seemed like an exception became a pattern. The outer solar system is not orderly in the way the inner system is. It is a dynamic, sculpted region shaped by migration, resonance, and gravitational scattering. Pluto is a product of this environment. Its orbit reflects the history of the solar system itself. Understanding Pluto's path also helps explain why it remained undiscovered for so long. Its tilted, elongated orbit keeps it far from the ecliptic plane where astronomers traditionally searched for planets. For much of its orbit, Pluto is faint, distant, and difficult to detect, and it was found only because its path brought it closer and brighter during the early 20th century. Pluto was discovered at the right time, not because it was dominant, but because it happened to be near its closest approach to the Sun. This timing bias shaped everything that followed. Had Pluto been discovered a few decades earlier or later, it might have been classified differently from the start. It might have been recognized as part of a broader population rather than elevated to planetary status. Chance played a role. But chance does not define nature, only our interpretation of it. Pluto's orbit also influences its climate. The extreme variation in distance from the Sun produces long, dramatic seasonal changes. As Pluto moves closer, ices sublimate, forming a thin atmosphere. As it moves away, that atmosphere freezes and falls back to the surface. These cycles occur over centuries, far beyond human experience. The orbit that once made Pluto seem problematic now makes it scientifically invaluable. It provides insight into processes that shape distant icy worlds. It reveals how resonance protects objects from chaos. It preserves evidence of planetary migration. Pluto's path is not a mistake. It is a message from the early solar system, written in motion. Pluto shows us that not all worlds follow the same rules, that planetary systems are shaped by violence as well as order, that categories built around inner worlds fail in the outer reaches. Pluto's strange orbit was never an embarrassment to planetary science. It was a clue. Pluto is not alone. For most of the 20th century, Pluto appeared to be an oddity, a single distant world circling the Sun in isolation. Its strange orbit, its small size, and its icy nature made it feel like an exception, a cosmic anomaly that defied easy explanation. This sense of isolation shaped everything scientists believed about Pluto. But isolation was an illusion. Beyond Neptune lies a vast region of space that remained hidden for decades. Not because it did not exist, but because it was too dark, too distant, and too faint to see. This region is now known as the Kuiper Belt, a broad disk of icy debris stretching from roughly 30 to 50 astronomical units from the Sun. Pluto lives here. The discovery of the Kuiper Belt transformed Pluto's story more profoundly than any reclassification ever could, when it revealed that Pluto was not a lone outcast at the edge of the solar system, but a prominent member of an enormous population of similar worlds. The Kuiper Belt is a relic of planetary formation. It is composed of material left over from the early solar system, ice-rich fragments that never merged into a large planet. In the inner regions, collisions and gravity built rocky worlds. Farther out, gas giants dominated. Beyond Neptune, the process stalled. Pluto formed in this stalled region. When astronomers began to detect Kuiper Belt objects in the 1990s, a new picture emerged. These objects shared Pluto's characteristics: small to medium size, icy composition, tilted and eccentric orbits, and frequent resonances with Neptune. Pluto was not unusual. It was representative. Some Kuiper Belt objects are nearly as large as Pluto. Others are smaller, but dynamically similar. Many follow resonant orbits, locked into gravitational patterns that mirror Pluto's relationship with Neptune. The solar system suddenly looked far more crowded than anyone had imagined. This realization forced scientists to rethink how the outer solar system works. Instead of a simple hierarchy of planets, it became clear that multiple populations coexist, each shaped by different processes. The Kuiper Belt is not a graveyard of debris. It is a structured, dynamic region. Objects within it interact gravitationally, migrate over time, and preserve records of the solar system's earliest moments. Pluto stands out within this population not because it is unique, but because it is large, complex, and accessible. It became the first Kuiper Belt object discovered, and therefore the symbol of the entire region. This symbolism created confusion. Because Pluto was known before its neighbors, it was treated as something separate. Once its neighbors were discovered, the truth became unavoidable. Pluto belongs to a class of worlds that had been invisible until recently. The realization that Pluto was not alone reframed its importance. Instead of diminishing it, this context elevated it. Pluto became a gateway, the first window into a region that holds clues to how planets form, migrate, and survive. The Kuiper Belt also explains Pluto's strange orbit. Neptune's outward migration during the early solar system scattered icy bodies into resonant configurations. Pluto was captured in one of these resonances, preserving its unusual path. This process affected countless objects. Some were scattered inward. Some were ejected entirely. Some were trapped, like Pluto. The Kuiper Belt is therefore a fossilized record of planetary migration. Studying Pluto and its neighbors allows scientists to reconstruct this chaotic past. Pluto's size makes it especially valuable. Larger bodies retain internal heat longer. They differentiate. They develop geology. Smaller bodies do not. Pluto is large enough to be geologically interesting. Many Kuiper Belt objects are too small to show complex behavior. Pluto, by contrast, preserves a full planetary history, internal structure, surface evolution, and atmospheric cycles, all within a Kuiper Belt environment. This makes Pluto a bridge between categories. It is not a planet in the classical sense. It is not a simple debris fragment. It occupies a middle ground. The discovery of the Kuiper Belt also changed how astronomers think about planetary systems beyond our own. Observations of debris disks around other stars suggest that Kuiper Belt-like structures are common. Pluto-like worlds may be widespread. Pluto is not a curiosity of our solar system. It is an example of a common outcome of planetary formation. Understanding Pluto helps us understand how systems evolve when planet formation does not proceed cleanly. It shows what happens when material remains beyond and the reach of dominant planets. The idea that Pluto is lesser because it is one of many misses the point entirely. Science does not value rarity over representativeness. In many cases, representative objects are more important. Pluto represents an entire population. Its story helps explain not only itself, but thousands of similar worlds. Its orbit, composition, and behavior provide a template for understanding the Kuiper Belt as a whole. The realization that Pluto is not alone also undermines the emotional argument against its reclassification. Pluto was never taken away. It was given a family. This family had simply been invisible. As detection methods improve, the Kuiper Belt continues to reveal its diversity. Objects with moons, objects with strange rotations, objects with unexpected compositions. Pluto is one among many, but remains one of the most accessible and informative. Pluto's neighbors validate the decision to rethink planetary categories. Without reclassification, the solar system would be conceptually cluttered. With it, relationships become clearer. Pluto's place is no longer ambiguous, or it is the most famous member of a vast, ancient population. A population that preserves the solar system's history in ice and rock. The dwarf planet that changed everything. When the term dwarf planet entered public conversation, it sounded like a compromise. a label created to soften a controversial decision. To many ears, it felt like a downgrade, a consolation prize for a world that had lost its place among the planets. But in scientific terms, the concept of a dwarf planet was anything but a compromise. It was a correction. The introduction of this category marked a turning point in how astronomers understood the solar system. It acknowledged something that had long been avoided. Not all round worlds that orbit the sun are the same kind of object. Some dominate their regions, others do not. Both can be complex. Both can be scientifically rich. The difference lies in context, not worth. Pluto became the most visible example of this realization. By placing Pluto in the dwarf planet category, scientists were not minimizing it. They were highlighting its true nature. A world shaped by a crowded, dynamic environment, rather than one that shaped its environment in return. This distinction matters because it reshapes how we interpret the solar system as a whole. Before Pluto, planetary science implicitly assumed a hierarchy. Planets were the main actors. Everything else was debris. The solar system appeared clean, ordered, and finished. Pluto shattered that illusion. The dwarf planet category acknowledges that planetary formation does not always produce clear winners. In some regions, material accumulates into dominant bodies. In others, it remains distributed among many smaller worlds. Both outcomes are natural. Pluto represents the second outcome. By recognizing this, astronomers gained a more accurate picture of the solar system's architecture. The outer regions were no longer seen as empty margins, but as active zones with their own rules and histories. Pluto's reclassification also forced scientists to reconsider what makes a world interesting. For centuries, size and dominance were assumed to correlate with importance. Large planets received attention. Small bodies were secondary. Pluto overturned that assumption. Despite its modest size, Pluto turned out to be geologically active, atmospherically dynamic, and internally complex. These traits are not exclusive to planets. They arise from internal energy, composition, and history. The dwarf planet category made space for this complexity. Instead of forcing Pluto into a planetary mold, scientists could now study it on its own terms. They could compare it to similar worlds. They could ask new questions about internal heat, surface renewal, and atmospheric cycles in small, icy bodies. Pluto expanded the scope of planetary science. The category also helped clarify debates beyond Pluto. Other dwarf planets, such as Eris, Haumea, and Makemake, displayed unique characteristics. Some were elongated, some rotated rapidly, some had moons and rings. These worlds did not fit neatly into the old framework. The dwarf planet concept allowed them to be recognized as coherent objects worthy of study. This recognition mattered. By the early 21st century, modern astronomers were discovering thousands of exoplanets around other stars. Many of these worlds fell outside traditional categories. Some were larger than Earth, but smaller than Neptune. Some orbited close to their stars. Some followed eccentric paths. Pluto's case had prepared science for this diversity. It taught astronomers to expect variation rather than conformity. It encouraged flexible classification, grounded in physics rather than tradition. Pluto did not just change how we view the outer solar system. It changed how we think about planets everywhere. The dwarf planet category also helped resolve confusion about boundaries. Without it, the word planet risked losing meaning. If everything round and orbiting a star were a planet, the category would become too broad to be useful. By refining definitions, science gained precision. This precision does not exclude wonder. It enhances it. Understanding what Pluto truly is makes it more fascinating. not less. It reveals how varied and surprising worlds can be, even at small scales. The emotional reaction to the term dwarf planet stemmed from misunderstanding. Many assumed it meant not a real planet. In reality, it means a different kind of planetary body. Pluto remains a planet in the broad sense, a planetary object. It simply belongs to a subclass defined by environment and dynamics. This nuance is often lost in public discussion, but it is central to scientific understanding. Pluto's influence on classification also underscores how science evolves. Categories are not fixed truths handed down by nature. They are tools refined as knowledge grows. Pluto forced refinement. It exposed the limitations of a planet-centric view of the solar system. It revealed that small worlds can be just as complex as large ones. It demonstrated that formation history matters as much as present-day appearance. In doing so, Pluto changed the question scientists ask. Instead of asking whether Pluto is really a planet, scientists now ask how dwarf planets form, how they evolve, and what they reveal about early solar system conditions. These questions are richer. They lead to deeper insight. Pluto's role in this shift cannot be overstated. It became the case study that justified an entire conceptual overhaul. Without Pluto, the need for such change might have been delayed for decades. Pluto did not lose status. It gained significance. By anchoring the dwarf planet category, Pluto became central to a new way of understanding planetary systems. It stands at the intersection of debris and planet, simplicity and complexity, past and present. It is both a remnant and a world. This duality is what makes Pluto so important. Pluto's hidden complexity. For most of its history and human awareness, Pluto was assumed to be simple. Small worlds were expected to be quiet worlds, frozen, inert, and unchanging. At such extreme distances from the sun, there seemed to be no source of energy capable of driving geological activity. No heat, no motion, no surprises. This assumption shaped everything. Pluto was imagined as a cosmic fossil, a leftover fragment preserved exactly as it formed billions of years ago. Scientists expected a cratered surface, dark and monotonous, shaped only by impacts and time. Whilst anything more seemed impossible, that expectation could not have been more wrong. Pluto is not simple, it is not inert, and it is certainly not dead. Beneath its frozen surface lies a world of unexpected complexity. A world that challenged nearly every assumption scientists had made about small, distant objects. Pluto's size initially misled researchers. At roughly 1/6 the mass of Earth's moon, it seemed too small to retain internal heat. Heat drives geology. Without it, planets and moons become static. This logic held true for many bodies in the solar system. Pluto defied it. The first clue came from density measurements. Pluto is denser than pure ice, but less dense than rock-dominated worlds. This suggests a mixed interior, a rocky core surrounded by an icy mantle. Such differentiation implies that Pluto once had enough heat to allow heavier materials to sink and lighter materials to rise. This alone was surprising. Differentiation requires energy. Either Pluto formed hot, or it retained heat longer than expected. In either case, the idea of Pluto as a simple frozen relic no longer fit. Models of Pluto's interior began to change. Scientists proposed that radioactive decay within its rocky core could provide a long-lasting heat source. Over billions of years, even a small amount of radioactive material can generate enough energy to maintain internal warmth. This heat would not melt Pluto entirely, but it could soften its interior, allowing slow movement beneath the surface. Such movement reshapes worlds. As heat causes ice to behave like rock, internal layers can shift. Ice can flow. Pressure builds. Cracks form. Surfaces renew. What appears frozen becomes dynamic over geological time. Pluto's complexity is not driven by violent volcanism or tectonic collisions like Earth's. It is driven by subtle, persistent processes acting over immense timescales. Slow does not mean insignificant. One of the most surprising aspects of Pluto is the apparent youth of some of its surface regions. Crater counts suggest that large areas have been resurfaced relatively recently in geological terms. This means something erased older impact marks. On a world so distant and cold, resurfacing should not happen. Yet it did. This resurfacing implies active processes, glacial flows of nitrogen ice, convective overturning of frozen layers, or even cryovolcanism, where slushy mixtures of ice and other materials erupt instead of molten rock. Pluto challenges Earth-centric intuition. On Earth, ice is brittle. On Pluto, ice can flow like syrup. Nitrogen ice, in particular, becomes soft at Pluto's temperatures. It can creep, spread, and reshape landscapes. This creates glaciers not of water, but of nitrogen and methane. Such glaciers transport material across the surface, filling craters and smoothing terrain. Over time, they erase evidence of impacts, giving the surface a younger appearance. This process requires energy. Not explosive energy, but sustained thermal gradients. Pluto's internal heat provides just enough. Pluto's complexity also extends to its seasonal cycles. Its extreme axial tilt and elongated orbit produce long, dramatic changes in sunlight distribution. As Pluto moves closer to the Sun, surface ices sublimate, forming a thin atmosphere. As it moves away, that atmosphere freezes and falls back to the ground. This cycle redistributes material across the planet. Nitrogen ice migrates. Methane accumulates in certain regions. Layers build and erode. Over centuries, these movements reshape the surface in subtle but profound ways. Pluto's surface is not static. It breathes. The idea that a world so small and distant could exhibit such behavior forced scientists to rethink assumptions about planetary activity. It suggested that size alone does not determine complexity. Composition and history matter just as much. Pluto's icy makeup is key. Ice behaves very differently from rock under pressure and temperature extremes. It can store and release energy in ways that rocky worlds cannot. Pluto's low gravity also plays a role. Materials move more easily. Mountains rise taller. Landscapes evolve under different rules. This combination, icy composition, internal heat, low gravity, and extreme seasons, produces a world unlike any other previously studied. Pluto is not a scaled-down planet. It is a different kind of world altogether. The realization of Pluto's complexity reframed its scientific value. Instead of being dismissed as a minor object, Pluto became a laboratory for understanding how icy bodies evolve. It offered insight into processes that may operate on countless similar worlds throughout the galaxy. Many exoplanets and exomoons likely exist in cold, distant regions around their stars. Pluto provides a nearby example of what such worlds might be like. Studying Pluto is therefore not just about understanding one object. It is about understanding a class of environments. Pluto also challenges the notion that geological activity requires proximity to a star. It shows that internal heat sources, even weak ones, can sustain activity far from stellar warmth. This has implications for habitability studies as well. While Pluto itself is far too cold for life as we know it, the processes that keep it active could operate on other icy worlds with subsurface oceans. Pluto's hidden complexity opens the door to broader questions. What other distant worlds are active? How long can small bodies retain heat? What kinds of geology exist beyond rock and lava? These questions expand planetary science beyond traditional boundaries. Pluto forces scientists to confront the limitations of Earth-based intuition. We are accustomed to judging worlds by familiar standards: size, temperature, composition. Our Pluto operates outside those standards. It teaches humility. The assumption that small worlds are simple has been permanently overturned. Pluto stands as proof that complexity can arise under unexpected conditions. This realization makes Pluto more important, not less. The dwarf planet label does not diminish Pluto's status as a world. It clarifies it. Pluto is a complex, evolving object shaped by unique forces. Its study informs theories of planetary formation, evolution, and diversity. Pluto is not what we imagined because our imagination was limited by experience. The surface no one expected for decades. Pluto was imagined as a dark, battered sphere, a frozen remnant scarred by billions of years of impacts. In this picture, its surface would be ancient, unchanged, and lifeless. There would be little to see, little to explain, and little to surprise. This expectation was logical. Small bodies, far from the sun, were assumed to be geologically dead. Without sunlight, without internal heat, without the violence of collisions or tectonic movement, there seemed to be no mechanism capable of reshaping the landscape. Pluto destroyed that assumption. When scientists finally saw Pluto's surface in detail, they did not see a graveyard. They saw a world still in motion. The most striking feature was a vast, bright region shaped like a heart. This region, later known as Sputnik Planitia, appeared smooth and largely free of impact craters. Its youth was unmistakable. Something had erased the scars of time. This alone was astonishing. Impact craters accumulate steadily. Without resurfacing, they remain indefinitely. A smooth surface implies recent activity. Activity that should not exist on a world like Pluto. Sputnik Planitia is not rock. It is ice, but not water ice in the way we understand it on Earth. It is dominated by nitrogen ice, mixed with methane and carbon monoxide. At Pluto's temperatures, nitrogen ice behaves like a viscous fluid. It can flow, spread, and convect. In effect, Pluto has glaciers. These glaciers do not grind rock. They reshape ice. They creep slowly, filling lowlands, smoothing terrain, and transporting material across the surface. Over long periods, this movement renews the landscape. The heart-shaped basin itself may be an ancient impact crater, later filled with ice that never stopped moving. As nitrogen ice slowly circulates, it erases evidence of the crater's violent origin. The circulation is driven by internal heat. Heat rises from below, warms the ice, and causes it to rise in cells, much like lava lamps on Earth. Cooler ice sinks, creating a slow but continuous overturn. This process, known as solid-state convection, operates over millions of years. It requires only modest energy. The existence of such a process on Pluto suggests that its interior is warmer than expected. Even small amounts of heat, sustained over long periods, can produce dramatic effects. Beyond Sputnik Planitia, Pluto's surface becomes more rugged. Mountains rise kilometers high, taller than many mountain ranges on Earth. These mountains are not made of rock, but of water ice, which at Pluto's temperatures is as hard as stone. Water ice forms Pluto's bedrock. These mountains appear young as well, and their sharp edges and lack of heavy cratering suggest recent formation. Some may have been uplifted by internal stresses. Others may be remnants of older crust exposed by glacial erosion. The idea that Pluto has mountains was once unthinkable. Mountains require strength and structure. They require a crust capable of supporting relief. Pluto's water ice crust provides this strength, acting as a rigid shell beneath softer, more mobile ices. This layered structure, rigid crust over flowing ice, enables complex geology. Pluto's surface also shows signs of tectonic activity. Long fractures and faults stretch across regions, suggesting that the crust has expanded. This expansion may be linked to freezing processes beneath the surface. If Pluto once had a subsurface ocean, or still does, its gradual freezing would cause expansion, cracking the crust. Even without a present ocean, partial melting and refreezing of ice layers could produce similar stresses. These features hint at an interior that has evolved over time rather than remaining static. Pluto's coloration adds another layer of mystery. Its surface displays a range of hues, from bright whites to deep reds and browns. These colors are not decorative. They are chemical signatures. Ultraviolet radiation from the sun interacts with methane in Pluto's atmosphere, producing complex organic molecules known as tholins. These compounds settle onto the surface, tinting it reddish-brown. Over time, these materials accumulate, altering surface reflectivity and temperature. Darker areas absorb more heat, affecting local ice behavior. This feedback loop further drives surface evolution, and Pluto's appearance is therefore shaped by both internal and external processes. Seasonal changes amplify this complexity. As Pluto moves closer to the sun, sunlight increases. Nitrogen ice sublimates, an atmosphere forms, winds redistribute material, frost migrates. As Pluto recedes, the atmosphere collapses. Gases freeze and fall back onto the surface, sometimes as snow. This cycle repeats over centuries. The surface is not frozen in time, it is slowly breathing. The absence of widespread cratering is perhaps the strongest evidence of activity. Some regions appear to be less than 10 million years old, a blink of an eye in geological terms. For a world billions of years old, this youth is shocking. It means Pluto has remained active for most of its existence. This activity does not require violent eruptions or molten rock. It relies on subtle physics, phase changes, slow flow, and internal heat distribution. It is quiet geology, but it is powerful. Pluto's surface tells a story of balance. Too little heat and everything freezes permanently. Too much heat and structures collapse. Pluto exists in between. This balance allows it to remain active far longer than expected. The discovery of such a surface changed how scientists think about icy worlds. If Pluto can be active, then many other distant objects may be as well. Worlds once dismissed as inert may harbor complexity beneath their frozen exteriors. Pluto forces a reevaluation of what geological activity requires. It also highlights how assumptions can mislead. For decades, Pluto was assumed to be simple because it was distant and small. That assumption delayed curiosity. Once curiosity returned, reality exceeded imagination. Pluto's surface is not a footnote in planetary science. It is a case study in how complexity emerges under extreme conditions. It shows that geology is not limited to warm, rocky worlds. Ice can shape landscapes. Cold can drive change. Time can amplify subtle forces. Pluto is proof. Ice that behaves like rock. On Earth, ice is fragile. It cracks under pressure, melts under warmth, and rarely lasts unchanged for long periods of time. It is temporary, a surface feature shaped by weather and seasons. We instinctively associate ice with weakness. On Pluto, that intuition fails completely. In the deep cold of the outer solar system, ice is not fragile. It is strong, structural, and dominant. At temperatures hovering around -200 degrees Celsius, water ice becomes as hard as granite. It forms Pluto's mountains, cliffs, and crust. It supports weight. It resists deformation. On Pluto, ice is rock. This reversal of familiar physics is essential to understanding why Pluto behaves the way it does. The same substances that are liquids or gases on Earth become solids there. Nitrogen, methane, and carbon monoxide freeze into thick layers that shape the surface. These ices are not static. They move, flow, and interact in ways that feel alien. Nitrogen ice is the most dynamic of Pluto's materials. At Pluto's surface temperatures, nitrogen ice is soft enough to deform under its own weight. Over time, it flows like a slow glacier, spreading across plains and filling depressions. This flow is driven by small temperature differences, internal heat, and seasonal sunlight. These glaciers are vast, and they move so slowly that change is invisible on human timescales. But over millions of years, they transform entire regions. Craters are filled, hills are smoothed, old features vanish beneath moving ice. Methane ice behaves differently. It is harder and more resistant to flow. It often accumulates at higher elevations, forming caps and ridges. These deposits influence how sunlight is absorbed and reflected, creating feedback loops that affect local temperatures. Carbon monoxide ice, though less abundant, plays a role in Pluto's atmospheric cycles. It sublimates easily, contributing to pressure changes and seasonal variation. Together, these ices create a complex system where surface chemistry, temperature, and geology interact continuously. The dominance of ice on Pluto explains why its surface can remain active without molten rock. Heat does not need to melt stone to reshape landscapes. It only needs to soften ice. This realization expanded planetary science. For a long time, geology was defined by rock, lava flows, tectonic plates, volcanic eruptions. Worlds that lacked these processes were considered dead. Pluto showed that geology does not require rock at all. It requires movement. Pluto's internal heat, though modest, is enough to drive slow convection in nitrogen ice. This convection brings warmer ice upward and cooler ice downward, creating cellular patterns across the surface. These patterns erase craters and renew terrain. Such processes blur the line between solid and fluid. Ice behaves like a very slow liquid, responding to gravity and heat over immense timescales. Pluto's low gravity enhances this effect. And with less gravitational force pressing materials down, ice deforms more easily. Mountains can grow taller. Glaciers can spread farther. Landscapes evolve under different constraints than on Earth. The idea that ice can form mountains feels counterintuitive because on Earth, ice collapses under its own weight. On Pluto, water ice is strong enough to support towering peaks. Nitrogen ice, though softer, forms vast plains. This division creates a layered world. A rigid crust of water ice supports a mobile veneer of volatile ices. Beneath that crust may lie warmer layers, possibly even a subsurface ocean kept liquid by internal heat and antifreeze compounds. This structure explains many of Pluto's features. Cracks in the crust, uplifted terrain, regions that appear to have collapsed or spread. All can be linked to interactions between rigid and mobile layers. Pluto's ice-driven geology challenges assumptions about habitability as well. While Pluto itself is too cold for life as we know it, the existence of long-lived internal heat suggests that other icy worlds could host subsurface environments. If heat can persist in a body as small as Pluto, it can persist elsewhere. Pluto becomes a proof of concept. The study of ice physics under extreme conditions has implications beyond Pluto. Many moons in the outer solar system, such as those orbiting Jupiter and Saturn, are ice-dominated. Understanding how ice behaves on Pluto informs how we interpret these worlds as well. Pluto also demonstrates that surface appearance can be misleading. What looks frozen and static may be slowly changing beneath the surface, and time stretches processes beyond immediate perception. Ice that appears solid may be flowing imperceptibly. This challenges the idea of dead worlds. Pluto is not dead. It is simply quiet. Its changes are measured in millions of years, not days. The chemistry of Pluto's ices also reveals how complex organic compounds form in cold environments. Tholins produced by radiation-driven reactions settle onto the surface, creating dark regions that absorb heat and influence ice behavior. This interaction between chemistry and physics creates feedback loops. Darker areas warm slightly, encouraging sublimation. Brighter areas reflect sunlight, preserving ice. Over time, these differences shape terrain. Pluto's ice is therefore not uniform. It is chemically diverse, physically dynamic, and geologically influential. The phrase "frozen world" fails to capture this reality. Pluto is frozen, but it is not static. Ice is the engine of change. Recognizing this required abandoning Earth-centric thinking. On Earth, ice is temporary. On Pluto, it is foundational. This inversion forces scientists to rethink how worlds are categorized and compared. Pluto does not fit into models designed for rocky planets. It requires new frameworks, ones that account for volatile, rich compositions and low-temperature physics. This is why Pluto is so valuable scientifically. It expands the range of known planetary behavior. It shows that the universe produces worlds that operate under rules unfamiliar to us. Understanding those rules requires patience and imagination. Pluto's ice behaves like rock because the environment demands it. Physics adapts to conditions, but there is nothing exceptional about this. Only our expectations were limited. Pluto did not break the laws of nature. It revealed their flexibility. Pluto's atmosphere shouldn't exist, by every rule scientists once relied on. Pluto should be airless. It is small. Its gravity is weak. Its temperature is extreme. Worlds like this are expected to lose their atmospheres early in their history. Gas molecules move faster in cold, low-gravity environments, escaping into space over time. This process strips small bodies bare, leaving behind frozen, lifeless surfaces. Pluto defies this expectation. Against all odds, Pluto possesses an atmosphere, thin, fragile, and temporary, but undeniably real. Its existence was one of the most unsettling surprises in the study of the outer solar system. For years, astronomers suspected Pluto might hold onto trace gases during certain parts of its orbit. Observations of starlight dimming as Pluto passed in front of distant stars hinted at something surrounding it. But the idea of a persistent atmosphere on such a small world remained controversial. Then the evidence became undeniable. Pluto's atmosphere is composed primarily of nitrogen, with traces of methane and carbon monoxide. These same substances dominate its surface ice. This connection is crucial, because Pluto's atmosphere is not permanent in the way Earth's is. It is seasonal. As Pluto moves closer to the Sun, even at its distant position, sunlight increases just enough to warm surface nitrogen ice. This ice sublimates, turning directly from solid to gas. The released gas forms a thin atmosphere that wraps the planet. And as Pluto moves farther away, temperatures drop. The atmosphere collapses. Gases freeze and snow back onto the surface. Pluto's atmosphere is not a stable envelope. It is a cycle. This cycle unfolds over centuries. Pluto's year lasts 248 Earth years. and its extreme axial tilt causes sunlight to fall unevenly across its surface. One hemisphere may bask in weak sunlight for decades, while the other remains in darkness. During these long seasons, ice migrates. Atmospheres grow and shrink. Pressure rises and falls. Pluto breathes. The pressure at Pluto's surface is tiny, a fraction of Earth's, comparable to the vacuum found high above our atmosphere. Yet even this whisper of gas is enough to shape Pluto's environment. Winds form, frost migrates, hazes develop high above the surface, while Pluto's atmosphere extends hundreds of kilometers into space. It is cold, layered, and structured. Temperature inversions create regions where temperature increases with altitude, a phenomenon once thought unlikely for such a thin atmosphere. One of the most surprising discoveries was the presence of haze layers, multiple thin sheets of suspended particles stacked high above Pluto's surface. These hazes are formed by sunlight breaking apart methane molecules, allowing complex hydrocarbons to form and clump together. These particles drift downward slowly, settling onto the surface and contributing to Pluto's reddish coloration. The atmosphere is therefore not separate from the surface. It is part of a continuous system. The fragility of Pluto's atmosphere makes it especially sensitive to change. Small shifts in temperature produce large changes in pressure. Slight variations in sunlight alter circulation patterns. The entire system responds delicately to orbital motion. This sensitivity makes Pluto a natural laboratory. Studying Pluto's atmosphere helps scientists understand how gases behave under extreme conditions. It provides insight into escape processes, photochemistry, and seasonal collapse, phenomena relevant to many worlds, including exoplanets. Pluto's atmosphere also raises questions about retention. How has it survived for billions of years? The answer lies in Pluto's coldness. While warmth accelerates atmospheric loss, extreme cold slows molecular motion. Pluto's atmosphere exists at the edge of escape, thick enough to exist temporarily, thin enough to vanish without constant replenishment. It is sustained by surface ice. As long as nitrogen ice remains, the atmosphere can return. This dynamic balance suggests that Pluto's atmosphere has likely existed many times throughout its history, appearing and disappearing as orbital conditions change. This makes Pluto's atmosphere less like Earth's and more like a seasonal phenomenon, a transient state rather than a permanent feature. The existence of such an atmosphere challenges the idea that small worlds are incapable of sustaining complex environments. Pluto proves that complexity does not require permanence. Temporary systems can still be rich and informative. Pluto's atmosphere also interacts with space itself. Solar radiation strips particles from the upper layers, creating a long tail of escaping gas. This slow loss contributes to Pluto's evolution over time. Yet the loss is not catastrophic. It is gradual. Pluto changes, but it endures. The discovery of Pluto's atmosphere also reframed how scientists think about other icy worlds. If Pluto can sustain an atmosphere, even temporarily, then similar processes may occur on other distant objects. This has implications for understanding the outer solar system and beyond. Pluto's atmosphere is not a failure of expectation. It is a correction. It shows that our intuition about what worlds can and cannot do is shaped by limited experience. Nature operates under a broader set of possibilities. Pluto's atmosphere exists because conditions align just enough to allow it. Weak gravity, extreme cold, volatile rich surfaces, and long seasons combine to create something unexpected. This combination is rare, but not unique. The lesson is not that Pluto is exceptional. It is that we underestimated what small worlds are capable of. Pluto's atmosphere is thin, but its implications are thick with meaning. It reveals that even distant, icy bodies can host complex, evolving systems that challenge simple classification. Pluto is not just frozen rock and ice. It is a world that exhales into space. Pluto and its moons. Pluto is not a solitary world drifting alone through the outer darkness. It exists within a small, tightly bound system, a miniature cosmos shaped by gravity, balance, and mutual influence. At the center of this system is a relationship unlike any other in the solar system. Pluto does not simply have a moon. It has a partner. Charon, Pluto's largest moon, is so massive relative to Pluto that the two bodies orbit a shared center of gravity located in the space between them. This point, known as the barycenter, lies outside Pluto's surface, a distinction that sets the Pluto-Charon system apart from every planet-moon pair in the solar system. In a very real sense, Pluto and Charon orbit each other. This makes them a binary system. Charon is more than half the diameter of Pluto and nearly 1/8 its mass. Compared to Earth's moon, which is about 1/4 Earth's diameter and far less massive relative to its planet, Charon is enormous. Its presence reshapes everything about Pluto's behavior. The discovery of Charon in 1978 was a turning point. For the first time, scientists could calculate Pluto's mass accurately by observing Charon's orbit. And this measurement revealed just how small Pluto truly was, and how misleading earlier assumptions had been. But Charon was not merely a measuring tool. It was a revelation. Charon's orbit is nearly circular and lies directly over Pluto's equator. The two bodies are tidally locked, meaning they always show the same face to each other. From Pluto's surface, Charon never rises or sets. It hangs in the same spot in the sky, looming large and motionless. From Charon, Pluto appears just as fixed. This mutual locking suggests a violent origin. The most widely accepted theory is that Pluto and Charon formed from a massive collision early in the solar system's history. Two icy bodies collided at low speed, ejecting material that later coalesced into Charon. Over time, tidal forces synchronized their rotations, and this scenario mirrors how Earth's moon is thought to have formed, but with a crucial difference: the mass ratio. The collision that formed Charon produced a near-equal pair, rather than a dominant planet and a small satellite. This outcome speaks to the chaotic conditions of the outer solar system, where relative speeds were lower and icy bodies more likely to merge gently rather than shatter. Charon's composition differs from Pluto's in important ways. It is dominated by water ice rather than volatile nitrogen and methane. This suggests that the two bodies originated from different layers of material or experienced different evolutionary paths after their formation. Charon's surface shows signs of tectonic fractures and ancient activity. Vast canyons stretch across its face, some deeper than the Grand Canyon on Earth, and these features indicate internal processes that once reshaped the moon. Charon, like Pluto, was not expected to be geologically interesting. It was. Beyond Charon, Pluto hosts 4 smaller moons: Styx, Nix, Kerberos, and Hydra. These moons are irregular in shape and chaotic in motion. They do not rotate smoothly like most moons. Instead, they tumble unpredictably, their rotations influenced by the combined gravity of Pluto and Charon. This chaotic motion is a direct consequence of the binary system. The gravitational field around Pluto is complex. The presence of two massive bodies creates regions of stability and instability. The smaller moons occupy narrow zones where they can survive without being ejected or colliding. Their existence tells a story of delicate balance, because these moons likely formed from debris created during the same collision that formed Charon. Over time, they settled into their current orbits, shaped by resonance and interaction. The Pluto system is therefore a record of early solar system violence preserved in miniature. Studying Pluto's moons provides insight into how binary systems form and evolve. Similar systems may exist elsewhere in the solar system and beyond, especially in regions where collisions are common and bodies are similar in size. The Pluto-Charon system challenges the notion that planets are solitary rulers with subordinate moons. It shows that gravitational partnerships can take many forms. Dominance is not always clear. Hierarchies can blur. This ambiguity further complicates Pluto's classification. If Pluto and Charon are a binary system, should Pluto even be considered the primary body? Some scientists have argued that Pluto and Charon should be classified together as a double dwarf planet system. This idea has not been formally adopted, but it highlights how Pluto resists simple labels. Pluto's moons also influence its environment. Charon's gravity affects Pluto's tides, internal stresses, and rotational dynamics. The mutual locking stabilizes their orientations, shaping climate patterns over long timescales. The smaller moons contribute dust and debris, interacting subtly with Pluto's atmosphere and surface. These interactions are minor, but over millions of years, even small effects accumulate. Pluto is therefore not an isolated object evolving independently. It is part of a system. This system context deepens Pluto's scientific value. Instead of studying a single world, scientists can examine interactions, how gravity shapes orbits, how collisions create moons, how binary dynamics influence evolution. The Pluto system becomes a microcosm of planetary formation processes. It also reinforces the idea that Pluto's story is not one of diminishment. Its reclassification did not strip it of complexity. If anything, it highlighted how unusual and informative Pluto truly is. A world with a massive companion, a system with chaotic moons, a history shaped by collision and balance. Pluto does not resemble the tidy textbook image of a planet. It resembles the universe itself, messy, dynamic, and full of exceptions. A world frozen in time, Pluto is not just distant in space. It is distant in time. While the inner solar system has been reshaped by heat, collisions, and constant change, Pluto has remained largely untouched by the forces that transform the worlds closer to the Sun. Its cold environment preserved materials and structures that vanished elsewhere long ago. Pluto is a survivor from the solar system's earliest chapter. When the Sun was young, the region beyond Neptune was a chaotic disk of ice and rock. Countless small bodies collided, merged, scattered, and migrated as the giant planets shifted their positions. Some material was flung outward, some was ejected entirely, some remained behind, trapped in stable orbits. Pluto formed in this ancient environment. Unlike Earth or Mars, Pluto never experienced global melting. It never differentiated into thick layers of molten rock and metal driven by intense heat. Instead, it cooled early, locking much of its original composition into place. This early freezing preserved a record. Pluto's interior retains clues about the materials present in the outer solar system billions of years ago. Its surface chemistry reflects primordial ices that have remained largely unchanged. Its isotopic ratios offer hints about the conditions under which it formed. In this sense, Pluto is a time capsule. Time capsules are valuable not because they are unchanged, but because they preserve context. Pluto has evolved, but it has done so slowly and gently. Its changes are layered atop ancient foundations. The craters on Pluto's older terrains record impacts from an era when collisions were more common. Their size and distribution provide insight into the population of early Kuiper Belt objects. These craters are fossils of a time when the solar system was still settling. Even the absence of craters tells a story. Regions like Sputnik Planitia lack ancient scars, suggesting resurfacing that erased them. This indicates not only activity, but timing. By determining which areas are young and which are old, scientists can reconstruct Pluto's geological timeline. This timeline stretches across billions of years. Pluto's extreme distance protected it from the violent reshaping that occurred closer to the Sun. The inner planets experienced massive impacts, volcanic flooding, and atmospheric loss. Pluto remained cold and stable, allowing it to retain volatile compounds that would have escaped elsewhere. These volatiles, nitrogen, methane, carbon monoxide, are relics of early solar system chemistry. On warmer worlds, they were driven off long ago. On Pluto, they remain. This makes Pluto a chemical archive. Studying these compounds reveals how materials were distributed in the young solar system. It helps scientists understand how planets acquired atmospheres, oceans, and organic molecules. Pluto's preservation also extends to its orbital configuration. Its resonance with Neptune is a frozen record of planetary migration. That resonance formed early and remained stable. By studying it, scientists can test models of how Neptune moved and how the Kuiper Belt was sculpted. Pluto is therefore not just a world. It is evidence. Evidence of migration, evidence of formation, evidence of survival. The idea that Pluto is frozen in time does not mean it is inactive. It means its activity operates on timescales that preserve history rather than erase it. Its slow geology modifies the surface without destroying the deeper record. This balance is rare, although many worlds either change too quickly or not at all. Pluto changes just enough to remain interesting while retaining its past. This makes Pluto invaluable for understanding planetary evolution. By comparing Pluto to other Kuiper Belt objects, scientists can identify which features are primordial and which are the result of later processes. Pluto serves as a reference point, a benchmark against which other distant worlds can be measured. The fact that Pluto is large enough to be geologically active, yet small enough to preserve ancient material places it in a unique category. It bridges eras. Pluto also helps scientists test theories about how icy worlds evolve over time. Does internal heat last long enough to drive activity for billions of years? Can small bodies retain subsurface oceans? How do volatile cycles shape surfaces? Pluto provides real-world data. Without Pluto, these questions would remain largely theoretical. The time capsule nature of Pluto extends beyond geology and chemistry. Its moons, especially Charon, also preserve early conditions. Their compositions, orbits, and fractures record the aftermath of ancient collisions. Together, Pluto and its moons form a system that has changed little since its formation. This preservation contrasts sharply with Earth, where plate tectonics, erosion, and biological activity continuously rewrite the surface. Earth forgets its past quickly. Pluto remembers. Memory in planetary science is rare. Pluto's memory allows scientists to peer back into the era when planets were still assembling. It offers a glimpse of processes that no longer operate in the inner solar system. In this sense, Pluto is not behind us, and it is behind everything else. The realization that Pluto is a time capsule reframes its importance. It is not defined by what it lacks compared to planets. It is defined by what it preserves that planets have lost. Pluto is valuable because it is old, because it remembers. The flyby that changed Pluto forever. For more than 80 years after its discovery, Pluto remained distant not just in space, but in understanding. It was a point of light, a calculation, a debate. Its surface was imagined. its nature inferred, its complexity suspected by some, dismissed by others. Then, in a single moment, Pluto became a world. The transformation did not come gradually. It arrived at high speed, after a journey that took nearly a decade, carried by a spacecraft that would never slow down or return. There would be no second chance, no orbit, and no long-term study from nearby. There would be one pass. That was all Pluto would allow. As the spacecraft approached, expectations were modest. Even after years of speculation, most scientists anticipated a heavily cratered surface, limited geological activity, and few surprises. The assumption of simplicity lingered to the end. The first images shattered it instantly. What appeared on scientists' screens was not a frozen relic, but a complex landscape filled with contrast. Smooth plains bordered rugged mountains. Bright regions stood beside dark, ancient terrains. Patterns emerged that had no precedent in the outer solar system. Pluto was alive. The most immediate shock was the absence of craters across large regions. The surface was young in geological terms, far younger than expected, and this alone forced a rethinking of Pluto's internal energy. Mountains rose where none should exist. Plains flowed where nothing should move. The surface told a story of motion, not stasis. As more data arrived, the scale of the revelation grew. Pluto's geology was not localized. It was global. Different regions displayed different ages, compositions, and histories. This diversity suggested that Pluto had not simply experienced a single resurfacing event, but ongoing processes operating over billions of years. The spacecraft revealed that Pluto's surface is shaped by cycles of ice, of atmosphere, of internal heat. These cycles operate slowly, but relentlessly. The heart-shaped region captured public attention, but it was only part of a larger picture. Surrounding terrains showed signs of tectonic stress, glacial movement, and complex layering. Pluto's crust appeared fractured in some areas, smooth in others, as if different forces had acted at different times. Pluto's topography defied expectations of scale. Some mountains reached heights comparable to major terrestrial ranges. Their existence implied a strong crust capable of supporting relief. A crust composed not of rock, but of water ice. This inversion of materials forced scientists to abandon Earth-based assumptions. On Pluto, the rules are different. The flyby also revealed Pluto's atmosphere in unprecedented detail. Layers of haze extended far above the surface, forming delicate bands that wrapped the planet. These layers shifted with altitude, indicating complex temperature structures. Such an atmosphere had never been observed on a world so small, and the interaction between Pluto's atmosphere and surface became clearer. Gases freeze and thaw. Particles form and settle. Energy moves slowly between layers, linking the planet's interior to space. The spacecraft's instruments detected signs of atmospheric escape. Particles drifting away under the influence of solar radiation. But the escape rate was lower than expected, suggesting that Pluto retains its atmosphere longer than models predicted. This finding implied a balance. Loss offset by replenishment over long timescales. Pluto's moons also came into focus. Charon's surface revealed ancient canyons and signs of past activity. Smaller moons showed irregular shapes and chaotic rotation, their motions influenced by the binary system's gravity. Together, these observations painted a picture of a dynamic system shaped by collision, through interaction, and time. The flyby forced scientists to confront how wrong their assumptions had been. Pluto was not a minor object at the fringe of the solar system. It was a complex, evolving world that demanded serious attention. This realization had ripple effects. If Pluto could be this active, what about other Kuiper Belt objects? What about distant icy worlds orbiting other stars? The flyby expanded the range of what scientists considered possible. Pluto became a benchmark. The encounter also highlighted the limits of remote observation. For decades, Pluto had been studied indirectly. Only by visiting it directly did its true nature emerge. This reinforced the importance of exploration in planetary science. Models and simulations are powerful tools, but they cannot replace observation. The flyby was bittersweet, and the spacecraft would never return. It would carry its data outward, into the Kuiper Belt and beyond, leaving Pluto behind. But Pluto had been changed permanently, not physically, but in human understanding. From that moment on, Pluto could no longer be dismissed as a footnote or casualty of classification. It had earned its place as one of the most fascinating worlds in the solar system. The flyby did not settle all questions. It raised many new ones. How long has Pluto been active? What drives its internal heat? Does it still harbor a subsurface ocean? How common are Pluto-like worlds elsewhere? These questions would guide research for decades. The encounter also changed the tone of the Pluto debate. Arguments about labels faded in importance. Attention shifted to substance. Pluto was no longer defined by what it was called, but by what it was. A world with history, a world with processes, a world with surprises. The flyby revealed something deeper as well. It showed that the outer solar system is not a graveyard. It is a realm of slow motion where change occurs quietly but persistently. Worlds evolve not through violence, but through patience. Pluto embodies this rhythm. The encounter was a reminder that discovery does not end with classification. It begins with curiosity, continues through exploration, and deepens through humility. Pluto taught us that the universe often hides its most profound truths behind distance and assumption. When we finally look closely, those truths reshape us. Why Pluto matters more than ever. After the flyby, Pluto could no longer be treated as a distant abstraction. It had become a place, a world with landscapes, history, and active processes. But its importance did not end with the revelation of its surface. In many ways, Pluto's relevance was only beginning. Pluto matters because it changed how scientists think. For decades, planetary science was shaped by a narrow set of assumptions drawn from the inner solar system. Planets were large. Activity required heat. Distance meant dormancy. Pluto quietly dismantled each of these ideas. It showed that small worlds can be active, that cold does not mean static, that distance does not imply insignificance. Pluto forced a re-examination of planetary evolution itself. One of the most important contributions Pluto makes to science is its role as a bridge between categories. It sits between planets and debris, between activity and dormancy, between past and present. And it embodies a middle state that had been largely ignored. By studying Pluto, scientists gain insight into how worlds behave when they do not follow the dominant pathways of formation. Not every system produces a neat set of planets. Most likely do not. Pluto represents a common outcome, a world that formed, differentiated, and evolved without becoming dominant. This outcome may be widespread throughout the galaxy. Many stars likely host belts of icy bodies similar to the Kuiper Belt. Pluto-like worlds may be far more common than Earth-like ones. Understanding Pluto therefore informs our understanding of planetary systems as a whole. Pluto also matters because it preserves information that other worlds have lost. Its cold environment slowed chemical reactions. Its gentle geology preserved ancient structures. when its surface retains signatures of early solar system conditions. Pluto is a record keeper. By analyzing its surface composition and isotopic ratios, scientists can test theories about how materials were distributed in the young solar system. They can compare Pluto's chemistry to that of comets and other icy bodies, building a more complete picture of early planetary formation. Pluto's orbit and resonance also matter. They provide direct evidence of giant planet migration, a process that likely shaped many planetary systems beyond our own. By understanding Pluto's path, scientists refine models of how planets move and how small bodies respond. Pluto helps validate those models. The dwarf planet also matters for understanding atmospheres. Pluto's fragile seasonal atmosphere exists at the edge of stability. Studying how it forms, collapses, and escapes provides insight into atmospheric loss processes that affect many worlds. These processes are relevant not only to distant icy bodies, but to rocky planets as well. Atmospheric escape played a role in shaping Mars, Venus, and Earth. Pluto offers a different regime in which to test the same physics. Pluto also reframed the search for life. While Pluto itself is inhospitable on the surface, the possibility of a subsurface ocean raises important questions. If internal heat can persist in a body as small as Pluto, then many icy worlds may host liquid environments beneath their surfaces. These environments could exist far from stars, powered by internal energy rather than sunlight. Pluto expanded the definition of where habitable conditions might arise. Even if Pluto does not host life, it helps identify where life could exist elsewhere. Pluto's importance also lies in how it reshaped scientific humility. The confidence with which Pluto was once dismissed stands in contrast to the caution that followed its close-up exploration. Scientists were reminded that inference has limits and that distance can conceal complexity. This lesson extends beyond Pluto. It applies to every distant world studied only through indirect observation. Pluto stands as a warning against premature conclusions and as an argument for exploration. The debate over Pluto's status also had a lasting impact. It sparked public interest in planetary science. It forced discussions about how science defines terms, revises knowledge, and handles uncertainty. Pluto became a teaching moment. Through Pluto, people learned that science is not a static list of facts. It is a process. It adapts as evidence accumulates. It changes its mind when necessary. This understanding is crucial in a time when misinformation spreads easily and certainty is often demanded prematurely. Pluto shows that changing one's mind is not weakness. It is progress. Pluto's continued importance is also practical. Data from the flyby is still being analyzed. New insights continue to emerge years after the encounter. Models are refined. Hypotheses are tested. Questions evolve. Pluto remains an active area of research. Future missions may one day return to Pluto, perhaps to orbit it, to land, or to study its atmosphere over time. Such missions would provide unprecedented insight into long-term processes operating in the outer solar system. Pluto is no longer out of reach. Technologically, it is challenging, but possible. Scientifically, it is compelling. Pluto's story has also influenced how scientists classify newly discovered worlds. The lessons learned from Pluto inform how exoplanets are categorized, how debris disks are interpreted, and how planetary diversity is embraced. Pluto taught scientists to expect the unexpected. The most important reason Pluto matters may be philosophical. It challenges hierarchy. For centuries, humans have ranked worlds by size, proximity, and familiarity. Pluto does not fit comfortably into such rankings. It forces us to confront the idea that importance is not dictated by dominance. A small world can matter enormously. Pluto's journey from planet to dwarf planet to complex world mirrors the journey of scientific understanding itself. Initial certainty gave way to doubt. Doubt led to re-examination. Re-examination led to deeper truth. Pluto is a case study in how knowledge grows. It reminds us that labels are temporary, that understanding is provisional, that humility is essential when confronting the universe. Pluto matters because it keeps asking questions. It asks how planets form. It asks how worlds evolve. It asks how much we truly know. And in doing so, it ensures that planetary science remains dynamic rather than complacent. The emotional side of science. The reaction to Pluto's reclassification revealed something that data alone never could. It revealed how deeply people connect to scientific ideas, not just as information, but as identity. Pluto was not merely an object in space. For many, it was a memory, a symbol, a familiar part of how the universe was learned and understood. When Pluto was reclassified, the response was not neutral, it was emotional. People did not argue about orbital dynamics or gravitational dominance. They argued about fairness, about loss, about tradition. Pluto became a stand-in for something much larger than itself. A feeling that knowledge was being rewritten, that something once certain was suddenly uncertain. This reaction surprised many scientists. From a scientific perspective, the change was straightforward. Definitions were refined, evidence was incorporated, understanding improved. Pluto did not change physically, only its category did. But science does not exist in isolation. It exists within culture. Pluto had been taught in classrooms for generations. It appeared in songs, cartoons, and mnemonic devices. Children learned its name early and stirred often before they understood what a planet truly was. Pluto became emotionally anchored to learning itself. When that anchor shifted, it felt personal. This reveals an important truth about science communication. Facts are not absorbed in a vacuum. They are woven into narratives, memories, and identity. When facts change, narratives must change too. And that process is uncomfortable. Pluto's case exposed this tension clearly. Many people felt that Pluto had been taken away. This language implied ownership, as if a scientific classification belonged to the public in the same way a cultural artifact does. But scientific knowledge is not owned. It evolves. The discomfort surrounding Pluto's reclassification also highlighted a misunderstanding about what science aims to do. Science does not aim to preserve familiar answers. It aims to produce accurate ones. When accuracy improves, answers may change. This change is not betrayal. It is the point. Pluto became a lesson in scientific humility, not just for scientists, but for everyone. It demonstrated that certainty is provisional, and that even long-held beliefs can be revised when new evidence appears. This lesson is difficult because it challenges a common expectation that learning produces permanent answers. In reality, learning produces better questions. Pluto also revealed how language shapes perception. The word dwarf carries emotional weight. It suggests smallness, inferiority, or loss. In astronomy, it is a technical term describing mass and dominance, not value. But language rarely stays technical outside of professional contexts. The term dwarf planet was misunderstood because it collided with everyday meaning. This collision fueled outrage more than the scientific reasoning itself. Had Pluto been labeled differently, the reaction might have been softer. This doesn't mean scientists should avoid technical terms. It means they must be aware of how those terms resonate beyond their intended context. Pluto's case sparked broader conversations about how science communicates change. How should revisions be explained? How can nuance be conveyed without triggering resistance? How can public trust be maintained when answers evolve? These questions matter far beyond astronomy. Pluto also became a rallying point for discussions about authority. Some people viewed the reclassification as an arbitrary decision made by a small group. This perception fueled skepticism, even though the process followed standard scientific practice. The debate highlighted the importance of transparency. When people understand why decisions are made, even if they disagree, trust improves. When decisions feel sudden or opaque, resistance grows. Pluto's reclassification was not sudden in scientific terms. It was the culmination of decades of discovery. But to the public, it appeared abrupt. This gap between scientific timescales and public awareness is a recurring challenge. Science moves slowly, then all at once. Pluto also revealed the power of symbols. Pluto was the smallest planet, the underdog, the last one. Removing it felt like erasing a narrative that celebrated inclusivity, that even the smallest world could belong. But science does not operate on narrative fairness. It operates on evidence. This does not make science cold, but it makes it honest. The emotional reaction to Pluto also underscored the need for education that emphasizes process over memorization. When students learn lists without understanding how those lists were formed, changes feel like corrections of mistakes rather than natural progress. If students learn that knowledge evolves, change feels expected. Pluto's story is therefore an opportunity. It can be used to teach not just astronomy, but how science works, how definitions are tools, how evidence accumulates, how certainty adjusts. Pluto humanized science. It showed that scientists debate, disagree, and revise, that they are not erasing knowledge, but refining it, that science is not a static authority, but a living conversation. This humanization is valuable. It builds resilience against misinformation. It fosters curiosity rather than fear. It encourages engagement rather than rejection. Pluto also revealed how much people care about space. The intensity of the reaction demonstrated that astronomy matters to the public, that distant worlds capture imagination, that people form attachments to cosmic concepts. This passion is a strength. It means science has an audience that cares deeply. Harnessing that passion requires empathy. Scientists must recognize emotional investment, even when it complicates communication. Pluto's case shows that facts alone are not enough. Context and care matter. The emotional side of Pluto's story does not diminish science. It enriches it. It reminds us that science is a human endeavor, conducted by people, learned by people, and interpreted by people. Emotion does not invalidate evidence. It coexists with it. Pluto stands at the intersection of evidence and emotion. It forced science to clarify definitions. It forced the public to confront change. It forced both to reflect on how knowledge is shared. This intersection is where understanding deepens. As we approach the conclusion of this journey, the focus will shift once more, from emotion back to perspective. With everything we now know, how should Pluto be seen? Not as a planet lost, but as a world revealed. Pluto's story is not about demotion, it is about discovery.